As we've heard, we have group theory, we're applying it to magnetism. There are different frameworks and methods that we can be using. We're using them to simplify the problems that we're dealing with. We can bring in Landau theory, and that's one of the things I'm going to do in this presentation. When we bring in Landau theory, we start creating rules. We start gaining this picture of what is allowed and what is not allowed, or what might be allowed under certain circumstances. As I said, history has left us with a wide variety of space groups. We have representation theory, and there's something called the method of Bertaut, which I'm going to be talking about next. But I want to expand upon Bertaut's original method and return to that of representation theory, connecting also with some of the work on space groups. We're going to start off with looking at representation analysis of magnetic structures, which was the title of one of Bertaut's papers back in 1968. In Bertaut's paper, he was concentrating on the application of the propagation vector. And he showed that magnetic space groups could be constructed from the character tables of irreducible representations of GK. So he gave us a firm mathematical link between magnetic space groups and representation theory. He then used a method of propagation to generate basis functions, which were these Fourier components that we saw in the first presentation. Bertaut's fundamental proposition was that the eigenfunctions of electrons in the periodic Hamiltonian are block waves, as we've been using in the earlier presentation. Magnetic structures are eigenfunctions of the spin-dependent electronic Hamiltonian and so have the same form. If we expand the exponential, we see it's made up of the real cosine and the imaginary sine part, as we saw earlier, and this formalism is very general. It can elegantly describe a wide variety of magnetic structures. And we have to remember that back in the 1960s, there was still a lot of discussion on what types of magnetic structure could exist. So that was also one of the goals of his work. We've seen that the basis functions could be complex and commensurate things. We can make helix structures, circular or elliptical, and this requires non-parallel components in those basis functions. We can work with basis functions that are complex or real, and we have to remember the relationship between imaginary and real basis functions. And we have to remember that basis functions are combined according to this simple linear summation. We have this coefficient. Just as the basis functions can be real or complex, so can that coefficient. The important thing is in the end of the summation that we finish with magnetic moments that are real. So if we have a basis function that is 1, 0, 0 and another that is entirely imaginary, these two may appear different, but actually they're the same because they're related by a simple multiplication by minus I. So they would be related by the coefficient here simply being minus I. So they actually correspond to the same basis function. They're equivalent. The linear combination of basis vectors can also involve complex numbers with a variety of phases. So here we have two basis functions related by complex conjugation. If we add them, we're going to end up with 2 times the real part of the basis function. And then we have these two, I pre-multiply them by minus I and I. And when we add them together, we're going to end up with 2 times the imaginary part of the basis functions. So it's important to think in terms of the coefficients when we're dealing with basis functions. And in a few minutes, I'll show you an interactive PDF that works with Full Prof Studio to help you understand how basis functions can be combined to make different magnetic structures. Now, back to the representation analysis, the method of Bertaut, as we like to call it. We know that we're starting with a space group of the crystal structure G0. K is a wave vector of our magnetic order. The subset of symmetry operations, and we only need the rotational part of the space group G0 that are compatible with the K vector, that leave it invariant with respect to a reciprocal lattice translation, form the space group of the little group GK. And we have the irreducible representations here. We can then use a method of projection where we can look at magnetic structures, axial vectors, and we can project out the basis functions associated with different irreducible representations. Now, at this point, I'd just like to have a quick look at what these basis functions look like. So here in this example, we have irreducible representation 1, 3, and 5. There is no 2. That would correspond to a situation where irreducible representation 2 did not appear in the decomposition of the magnetic representation. So there is no magnetic structure compatible with irreducible representation 2 for a magnetic moment at the particular site in question. If we look at irreducible representation 1, the components here are with respect to the natural axes of the system. So these are the space group axes, the unit cell axes, rather than being in Cartesian. We have A, B, and C components. The C components here are the same size, but they're plus and minus. So this would correspond to an antiferromagnetic relationship between those C components. 6 is not something you can worry about, because remember, when we combine basis functions, we have the right, or we should multiply them by a coefficient. So you could multiply these by 1 on 6 and turn that into 0, 0, 1 and 0, 0, minus 1. It doesn't make any difference. The important thing is that in the end, your magnetic structure has moments that are of a particular size. So if you downscale the size of the basis functions, you'll simply be upscaling the size of the coefficients. If we look at the next irreducible representation, number 3, we again see only C components, now 6 and 6. So that will correspond to ferromagnetism, with both the components along the C direction being the same size. Irreducible representation 5 now involves 4 basis functions. Now this is starting to get a little bit more complicated to understand, because if you combine all of these basis functions, what's important is that it recreates all of the degrees of freedom of our system. We have 2 magnetic atoms, or atoms at 2 symmetry-related positions. Each magnetic moment has 3 degrees of freedom, so with 2 atoms, we're going to have 2 times 3, which is 6 degrees of freedom in our question. Our first one was antiferromagnetic along C. Our next one is ferromagnetic along C, but we still have another 4 degrees of freedom left. And these 4 degrees of freedom have to create all of the other structures that are not in these irreducible representations, because irreducible representations represent orthogonal structures. So if we have ferro the same size in this one and antiferro the same size in this one, here we have to have everything else that's possible in the AB plane. There are no components along the C direction here, because if you combine irreducible representation 1, irreducible representation 3, you're combining ferromagnetic array with antiferromagnetic array. So combinations of that will lead to components along C of all differing sizes. So the components along C are already covered by the first 2 irreducible representations. Number 5, you can imagine, is everything else happening in the AB plane. So what we're seeing is that all the symmetry does is help us classify degrees of freedom. It doesn't make the rules. The rules have to come from somewhere else. And Landau theory is historically one of the most important frameworks for rules. In fact, it's the reference. But it's useful, or I would say important, to remember that a lot of the early work applying Landau theory to magnetic structures were coming from a position of trying to predict possible magnetic structures. The rules were originally designed for prediction, and it makes a little bit of difference if we're working back the other way from a sample that we have data on, and we're trying to work out what the magnetic ordering corresponds to. So H, your Hamiltonian, may appear to break some of these rules, but that may simply be because the transition is simply not as simple as you think it is. So give that as a warning, but let's move on. Let's have a quick introduction to Landau theory for second-order phase transitions. So for second-order phase transitions, we have some form of coordinate system Q. And if you do the derivative of the free energy with respect to Q, that should be equal to 0. And it should correspond to a minimum free energy, so the second derivative is greater than 0. The free energy will vary continuously as a function of temperature, but the symmetry change isn't continuous. Suddenly symmetry is broken. You can't break a little bit of the symmetry, or you can't break a little bit of a symmetry operation. Now we'll assume that the free energy can be expanded as a function of an order parameter. That's what Q corresponds to. And it will have temperature-dependent coefficients. So now this order parameter Q could involve polarization, strain, mixing coefficients of our magnetic structures or our basis functions. The minima can also change as a function of temperature. Now what we're going to be doing is expanding the free energy in terms of this power series in this coordinate Q, the order parameter. As you cool it down, the system changes from one that's parabolic, this is above the ordering temperature, and it develops minima when you go below the ordering transition. The condition that the free energy of minus Q is the same as Q means that it's symmetric with regards to Q. And it also requires that the power series can only contain even powers of Q. This means that we're left with a power series that can still go on a very long way, but we tend to truncate the power series as soon as practically possible. And that truncation will lead to assumptions. If you start truncating things at second order, Q squared, or at fourth order, you're going to get different results than doing it to the eighth order, but the equations start getting very, very complicated very, very quickly. This allows us to create a mathematical system of representation analysis using free energy invariance. We have to think in terms of groups and subgroups, but this is still a mathematical process based on representation theory. According to Landau theory, the symmetry group of the magnetic structure should be a subgroup of the space group before the phase transition. Typically, the transition should involve a single irreducible representation of that G0. Now, the transition should involve a single irreducible representation of that space group. If we're looking at magnetic structures, very often we have a magnetic structure with a non-zero propagation vector. So we have a star with a number of arms in it. And you can combine the arms of the star according to the symmetry operations that cause them to be symmetry related and combine them to make this overall space group symmetry G0, which is also called the full group if you're comparing it to the literature. So the rotationally related irreducible representations of the set of propagation vectors, each with its own GK, come together and define a collection of matrices that pull all of these GK descriptions together. So all of the arms of the star contribute to making an overall set of matrices, and said this is the full group, and it corresponds to all of the operations of the space group. And it's in this space that Landau says we have this phase transition and we consider only one irreducible representation becoming critical or driving the transition. Now, Bertaut moved away from this full group, this G0 space group, and instead focused on the group of the propagation vector. He did it because in many cases, a single irreducible representation of GK is a good starting point. Many magnetic structures involve only a single propagation vector being involved rather than all of the arms of the star. And instead, we see domains within our sample that corresponds to the broken symmetry that happens when we do this. And if you're using GK, there can still be coupling between the irreducible representations, and this can lead to isotropy groups within magnetic space group, magnetic point group theory, and a similar type of thing happens within GK. Now back to Landau theory and free energy. He was defining a free energy in terms of these order parameters Q. Now we can write this as a summation. So we're writing our power series here. And I'm changing the notation away from Q to being eta. We're using eta because eta is now an order parameter defined in terms of the mixing coefficients that we're using to combine our basis functions. So just as we combine our block waves by these mixing coefficients to make the magnetic moment, these mixing coefficients have physical meaning within Landau theory and are valid order parameters to go into this free energy expansion. But rather than dealing with just one coefficient at a time, we use a vector of them where we're combining all of the relevant basis functions. So we have an order parameter description that's based on our basis vector combinations through these mixing coefficients. So during a phase transition, the symmetry group changes from some parent group to some subgroup H, and that should be a group of the irreducible representation or a subgroup of it. And that's what I just want to explore now. This is an example where we have two coefficients. What we're doing is combining two basis functions within a single irreducible representation. So the mixing of those two coefficients defined a particular symmetry space just within the irreducible representations themselves. We're considering space within irreducible representations. So different coefficients can correspond to structures that have different symmetry operations. despite the fact that they are still within the same irreducible representation. So we can end up with high symmetry and low symmetry structures within a multidimensional space of basis functions associated with an irreducible representation. So in this slide, we're going to be looking at magnetic space groups, magnetic point groups, and how we can couple between these IRs using this vector of mixing coefficients. So for a given eta, which is our combined order parameter, and a particular reduced representation, we have to list the symmetry operations that leave this vector invariant or reverse it. And these can be used to create our magnetic point groups and our magnetic space groups. In the language of Landau, this set of eta are a set of symmetry-related order parameters. You can have different types of order parameters available within an irreducible representation, depending on the irreducible representations and matrix values themselves. In general, I would like to call these vectors stationary vectors rather than isotropy vectors, because it makes a relationship to direct space and reciprocal space where we have the same type of structures. In real space, the stationary vectors are particular vectors that correspond to the special positions in the crystal structure. In reciprocal space, the vectors that are left unchanged is the propagation vector, and the stationary vectors correspond to the points of the Brillouin zone, or the lines of the Brillouin zone. The space that we're working with is inside the irreducible representation itself. The set of stationary vectors defines a unique collection of magnetic point groups and magnetic space groups within an irreducible representation. If we have two representations that contain the same matrices within them, then it's possible for magnetic point groups and magnetic space groups to occur in different irreducible representations. A trivial case would be a symmetry that would just the identity operation. Now, if you have the same symmetry group across different irreducible representations, then it means that their symmetries can be coupled together, and this coupling may happen according to one irreducible representation that's being the main drive for the transition. So we call this a primary irreducible representation, and another that gets induced through coupling. So we have a secondary order parameter as well. So you have two irreducible representations coupling together, despite the fact that their degrees of freedom are orthogonal. And this happens because they share the same symmetry. So it tells us about coupling. If we look back at some of this complexity, we start off with irreducible representations. We're dealing with space groups, so we can have dimensions of matrices of 1 to 6. If we have irreducible representations of order 1, the matrix representatives themselves across all the symmetry operations are going to be 1 or -1. Because we're dealing with simple K vectors, there's no phasing involved yet. The phasing is just unity. These can be used to help us construct magnetic space groups. If we have irreducible representations of order 2 or greater, these matrices are irreducible. They can't be reduced any further. Together, they create a generalized symmetry space that doesn't necessarily correspond to a single magnetic space group. It could be that higher symmetry structures are possible within this overall symmetry space. These high symmetry structures can be defined using magnetic point groups or magnetic space groups. Starting to pull these ideas together, making a more general bridge using different tools of representation theory. So going beyond Bertaut's original theory, our refinement strategy would begin by determining the space group of the crystal structure. We need the propagation vector for the magnetic transition, assuming one propagation vector at the moment. We would calculate the irreducible representations for that space group and that propagation vector. So these are the irreducible representations of the space group GK. And we project out the basis functions. These basis functions, when we have more complicated sets, such as here for irreducible representation 5, which is a two-dimensional irreducible representation, creates an overall space that itself could have higher symmetry subspaces. So these would be isotropy groups, if you want to use that language, but we can just think of them as being higher symmetry spaces. We can stay within the description that we're using in terms of mixing coefficients, and we can define these spaces using those mixing coefficients, because that's what these eta vectors correspond to. And we can define the magnetic point groups directly from the symmetry operations that we have here at the top, and seeing which ones leave that vector invariant or turn it into minus eta. So we can define magnetic point groups, G, K, and minus K, the ones that reverse the vector. So we can carry on with a structure where we can refine directly in terms of mixing coefficients. So we can refine directly in terms of these order parameter vectors, but we can look at these high symmetry structures in turn, or we can look at the entire symmetry space of the irreducible representation. This is the last slide I'd like to leave you with for Landau theory. There may be times it appears not to work. And this can happen when the model that you're using simply doesn't have the sophistication or the number of terms required to demonstrate what is actually happening. Still, when it appears to be broken, you can still start with irreducible representations to understand how they can classify symmetry types. You may discover in analyzing your data that several irreducible representations are involved in magnetic transition, and this can help you think about coupling terms and to help think about what is actually happening that's causing those irreducible representations to mix. If you were refining magnetic structures using other techniques, you may not notice that different irreducible representations are combining to give that overall magnetic structure. There can also be a difference between having transitions that are strongly second order and strongly first order and everything in between. When you're looking at your magnetic structure, you should be thinking about different aspects of the Hamiltonian, large aspects that define key features, but there may be other features that are smaller, that are driven by smaller terms in the Hamiltonian. What symmetry and Landau theory are doing are giving you a language with which to understand how these things come together and how they may be operating in the material that you're working with.